All right, we are now recording. Let's get the slideshow set up from current slide. And here we go. All right. There is an announcement going on the board right now for those of you who are not here. Scholarship Summit is happening in the ACAT building on October the 11th from 1 to 3 p.m. That's on the Birmingham West Campus. And it'll be in our Ethel Hall building, which is right across the parking lot from our classroom here. And this will be October the 12th, which, let's see, what day October 12th is.
It's a Wednesday.
A Wednesday. Yeah, 1 week from today. And that will be here on the Bessemer campus. You try that other darkening on there. That'll work. These things dry out so fast. And the one on the Bessemer campus is also 1 to 3 in the afternoon. Yeah, so next Tuesday.
I'll probably, sometime towards the end of this class on Wednesday, I'll go ahead and leave and go to that.
Right. Okay. All right. And here's Victor.
We're talking about makers again today.
Yes. And there's a scholarship summit coming up next week, Tuesday on Birmingham West Campus, Wednesday on this campus.
Have you seen Airplane? The movie Airplane? The exclamation point after? Okay. That's where that joke comes from.
Oh.
I'll have to show you a video or something.
All right.
I hope you understand.
Okay. Now.
This is from 12:06. Or are we on?
Yeah, we're in 12.5. We're finishing up 12.5. The last thing we did was,
Example 2?
well, I'm sorry. We finished example 2. The last thing on the slide was this. In case you're wondering, this was from example 2. Okay? I've got that we actually finished example 3 also, and we're getting ready to start example 4. Is that what you got, basically?
Example 3?
Yeah, that we finished example 3. Did you have that we did?
I'm trying to find my place. Just hope I've got here we go. Maybe. It'll be. This is 12.5, right?
12.5.
Yeah, I have us through example 3 and.
Yeah, I had that we finished example 3. Did you have that we finished it?
Yeah.
Yeah, okay. So we're starting example 4 on page 667. And this was the last part of example 2, so there was nothing on example 3 there, but I'm going to use the white space. Here's example 4. Intersection of a plane and a line. What we're asked for is find the point P. This is what we're looking for. Let me get my pen set up here. Okay, we're looking for a point P, okay, where the plane (3x minus 9y plus 2z equals 7). 3x minus 9y plus 2z equals 7. That's a plane, right? What makes that a plane?
The form.
Okay, what's about the form?
It's something X plus something Y, something Z equals something.
Okay, and it's linear in X, Y, and Z.
Yes.
That's the key.
All
Right.
first order.
All first order, okay? First degree, okay? You're in differential equations, okay? All right, so yeah, you got 3 variables there that basically set you in the 3 space, but they're all linear expressions in 3 space, and that puts you on a plane. Okay? Now, we're looking for a point that's got to be on that plane, by the way, too, but where that plane and the line r of t, now this is written in vector form, r of t, which is equal to, this is one way to express it, 1, 2, 1. There's a vector plus a parameter t times vector negative 2, 0, 1. Okay. Where those two intersect. And my goodness, I'm freezing in here. All right. Okay. So we're looking for the single point P, supposedly on this one, where that plane intersects with this vector. All right. Let's see. What would be a good approach to that?
Can't really do it graphically.
Yeah, graphically sort of stinks, okay? It'd be really hard to do, but let's see if we can think of a way that this would make sense. Now, one thing we could get right off the top, not that it's any helpful, you could get the normal to that plane. But I'm not sure that's really helpful. Can't think of how it would be right now. But every point on the plane satisfies that equation, and every point on the line satisfies this equation.
You gotta find where a point that satisfies both.
Yeah, we want the point that satisfies both of those. So the trouble is so here might be a way. Writing this line in
T is
parametric
scalar.
equation. Say again, what were you going to say?
I was asking, is T just a scalar, like a number?
Yeah, T is in a sense a variable. Okay, different values of t that would give different points on the line. That's what I was getting at. The point 1 minus 2t is always going to be an x-coordinate on this line, right? And 2 is always going to be the y-coordinate. Guess what? 2 is going to be the y-coordinate, okay? Because all the 2's on this line are all the y-coordinates on that line is 2, R2, okay? And 1 plus t is going to be the z-coordinate. So why don't we take those and plug them in that and see what we get t to be. And once we have that, then we can identify the point where that's true. I think that will work. Doesn't it seem like that would make sense?
Yeah, so basically go ahead and distribute out and do the vector addition there.
Right, that's it. Because this is saying R of t, that line represented that. The x-coordinate of it is 1 minus 2t, so that means 3 times a 1 minus 2t, minus 9 times, and the y-coordinate or component of that vector, every place is 2, okay, because it's plus 0t. 9 times 2, plus 2 times, and the z component of that vector r is going to be 1 plus t. 1 plus t. And to be on the plane, that thing has to equal 7. So the parametric equations guarantee it's on the line, and the fact that those plugged into that equation guarantees it's on the plane.
So we can
So let's see what we get.
Add over a 18, right?
Say that again.
So we can go ahead and add an 18 over, right?
Right. Yeah, we can do that now if you want to. Plus 18 will be, plus 18 would be 25. Okay, we'll get there in a second. So this will be 3 minus 6t, and we've already taken care of the 18, so it's out of there. Plus 2 plus 2t is equal to 18. That was what you, no, equal 25. Sorry. Yeah, I just wrote it down. I didn't add it. Equal 25. Does that make sense? Now let's combine like terms. And that gives you negative 4t plus 5, so let's subtract the 5 from both sides, is equal to 20. I skipped a bunch of steps there. Was that okay? Goodness gracious. I skipped steps, it skipped slides, okay? I was just trying to conserve a little room here. 2 plus 3 is 5, subtract that from both sides, that gives you 20. And this will be a minus 4t is equal to 20.
So t equals -5.
T is equal to negative 5. That is the place on that line where it intersects the plane. T is equal to negative 5. So plugging that in, so we want the point P, and I guess the easiest place to do that would be P would then be equal, and it's a point, so those are parentheses, that would be 1 minus 2 times negative 5, that would be plus 10, that would be 11. 2, it's got to be a 2, and it's got to be 1 minus 5 is negative 4. That looks like to me that would be the point P. Now,
Okay,
did I do something wrong?
no,
Oh, okay.
I'm just trying to see.
Oh, how I got that?
Yeah, a little bit.
I plugged it in here. This is my parametric equation in T.
Okay, and you distribute the -5 and then add it.
Right.
Okay.
Okay, I should have taken the step and done that. But let's see if that's indeed true. If we do this, that will be 33 minus 18, I think that would be 15, minus 8, sure enough, is 7. So it's on the plane. And I think we just verified that when t is equal to negative 5, it's on the line. So yeah, I think that. Okay, does that make sense?
No,
Okay, you see what we did there?
I got there.
You got the answer. All right, so you agree with us. Okay, let's see what the book got. The plane and the line intersect at the point 11 to negative 4. Okay, now did they do about it any? No, I think they did it just about the same way that we did. The line has those parametric equations. Okay, 1 minus 2, x equal 1 minus 2t, y is equal to 2, and z is equal to 1 plus t. That comes from the r of t. And you put those values in to your plane equation, 3x minus 9y plus 2t, 2z is equal to 7, and solve for t. Go back and plug in to your parametric line equation and see what point you have that does it. Now, little definition here. The intersection of a plane, that's that funny looking P they do there, not the point P, but the plane P, which isn't too plain, it's fancy. With the coordinate plane, the intersection of a plane with a coordinate plane. What in the world do we mean by a coordinate plane? by a coordinate plane.
Well, X and Y plane.
What's that?
An X and Y plane?
That's one of them.
Or
A coordinate plane is the XY plane, the YZ plane, or the XZ plane. Right. It's one of those planes. That's what we mean by a coordinate plane. So the intersection of any old plane with a coordinate plane or a plane parallel to a coordinate plane. Okay? However they would be going. Okay?
Kind of like how, well, Y equal to 2 would have like this.
Okay, yeah.
Yeah,
Depends on which way your y-axis is. If this is your x-axis, there's your y-axis, and here's your z-axis. Y is equal to 2 would be a plane here.
So
Y is equal to 13 would be a plane there. Those are parallel to the coordinate plane.
So what we just did was parallel to a coordinate.
The y component, this line right here is on the plane y is equal to 2. You're absolutely right. This line here. It's not a plane itself. It's a line on that plane. Okay? It's going
Oh,
some
yeah,
way.
because the plane was different. It was the line that was on the plane.
Right, yeah. Okay. Yeah, that's exactly right. Okay. Yeah, the plane was slicing somehow. I don't know how. I never can have a good idea where those are slicing. Okay, so the intersection of a plane P with a coordinate plane or a plane parallel to a coordinate plane is called a trace. Now, the next section, that's one reason I'm really harping on this. Next section we'll be talking about traces a lot more. The trace is a line unless the plane P is parallel to a coordinate plane, in which case the trace is empty or is the plane itself. Okay. All right. So, example 5 talks about traces of the plane. It says, graph the plane, yeah, right, negative 2x plus 3y plus z is equal to 6, and then find its traces on the coordinate planes, just the 3 coordinate planes. No, yeah.
I'll go ahead and say, unless you plan on asking us to graph it, I don't want to.
Okay. Who cares about what you want? Okay. So what we're going to do here is I'm going to show you how they graph it. But I'll try to also fill that in a little bit because it is somewhat of a pain in the neck. But you might have to do it not in this course, but somewhere else. I don't know.
I don't think that's the graph. Is it?
I don't know either. No, that doesn't look like it, does it? Let's just, no, that's a completely different.
That's for a previous exam. Let's see if it's on the next slide.
Okay, was that the one we just did? We didn't do any
No,
cross product.
That was like example 2 or 3.
Yeah, that was back. I'm sorry. Okay, that's the one. This is the one for this one, I believe. Okay, and I'll give you a little bit of a few suggestions of how you plot this. Okay, it says graph the plane negative 2x minus 3y plus z is equal to 6. Then find its traces on the coordinate plane. Okay, now, yeah, that's the same one. How I would start is that normal vector. The normal vector to this plane is minus 2 in the x direction, back that way, plus 3 in the y direction, I'm sorry, that's out this way, and plus 1 in the z direction, okay? So a minus 2 in x plus 3 in y plus 1 in z, okay? So that would be a plane that goes something like that, you know, back in x twice, 3 times that way, and 1 times up. So something about, I don't have to be down there, but something about like that. That's the plane. So the plane parallel, normal to that would have to be a plane like this. Now they have obviously twisted their x and y around to bring it this way. So the way they've done it here, here's the origin, minus 1x plus 2y and plus 1z. That's the plane, the vector coming out this way, and this is the plane that's perpendicular to that. Awfully hard to draw in two space. Okay. Draw a three-dimensional thing on two space. But you can also do this. When x is equal to 0, okay, x is equal to 0, and y is equal to 0, then that's going to be at the place where it intersects, and that's obvious z is equal to 6, right there. That plane intersects the z-axis right there. When these two are 0, x is equal to -3. There that point is. And when done these two, okay, when these two are 0, then y is equal to 2. Come out here too. So that gives you, you got sort of the feel for the normal. This gives you 3 points there, okay? And then connecting this point with that point, y is equal to 2, z is equal to 6, x is still 0, right? So therefore, this is the line. That line right there is the trace on the YZ plane. Here's the YZ plane. X stays 0. So the YZ plane, there's the line that traces there. Now, we haven't defined it yet. Oh, but it's not hard to. X is equal to 0. There it is. 3x plus 2z is equal to 6. 3x plus 2z is equal to 6. Okay? And on the xz plane, y is 0 equal to 0, so that's -2x plus z is equal to 6. And on the xy plane, you got -2x plus 3y is equal to 6, and that's the one down here. -2x plus 3y is equal to 6. So it's real easy to come up with those lines, thinking about what they are. Drawing the plane is a lot harder, but coming up with those 3 lines. And that was the second part of the question. Find the traces on the coordinate plane. So the coordinate plane being xy plane, that's where z is equal to 0. There's the, I mean, there it is, right there. On the xz plane, that's where y is equal to 0. There's the, is that it? Yeah, xz plane, that's the one. And then the one where x equals 0, that's in the yz plane. There it is there. 3y plus z is equal to 6. So that wasn't probably, coming up with equations of lines really is not bad. On the plane. Now, if it wasn't on that plane, but on the plane like x equal 2, you know, where is it? Do that. Just put x equal 2 here. Now, solve that. You know, that would be a -4, add that would be x, that would be this line right here equal to 10. Okay. So, I mean, you could just do that wherever, whichever plane you want that to be trace, whichever plane you want the trace to reside. Okay. All right. Any questions about that? That, I think, does end 12.5. In here. Okay. Preliminary question. What is the equation of the plane? The equation of the plane. Let's see, no, this is not here. Okay. What is the equation of the plane parallel to, that means parallel to 3x plus 4y minus z is equal to 5. 3x minus, no, plus 4y minus z equal 5. That's the plane, obviously, right? That passes through the origin. What is the equation of the plane parallel to that plane that passes through the origin? Now, what do you think it means to be parallel to that plane?
It has to be the exact same on the left, a different on the right.
Okay, is that what you're going to say? Okay.
Equal to a different constant.
Okay, now that, I like the way you say that. Here's how I think about it, which is saying the same thing. It's got to have, it's parallel to that plane, this plane, wherever it is. Let's say it's that plane, that the plane parallel to that has the same normal line, right? That's the best way you can talk about it, is this normal line. If it's parallel to that, the normal line's the same, right? So guess what? These are all the same. Okay, the coefficients of that are the same, and then that means it has the same, it's just a different number at the end. And if it's passing through the origin, what's that number got to be? The big fat 0. Okay, don't think of that on your test set. Okay, and that would be the, this thing is equal to 0. Better be the answer they have in the back, otherwise we'll be screaming at them, okay? Or at least I will. Okay, this is 12.5.
Yeah, I figure.
Yes.
The big fat and then that 0 on one of our answers.
What's that?
You want us to write out the big fat
Yeah,
0?
right. Yes, except we shouldn't be making fun of 0. It may be sensitive about its weight, so we won't do that. All right.
Especially compared to infinity.
Right. Okay. It's too big fat. No. All right. Now, number 2. The vector k, I'll write the answer down here in case some of you listening at home. 3x plus 4y minus z is equal to 0. Parallel to that, meaning it has the same normal line passing through the origin, that means the sum of those have to be 0. Okay. Number 2, the vector k is normal to which of the following planes? Normal to which of the following planes?
Wouldn't that be, I'll wait till you write it.
Vector k is normal to which plane?
Alright, so I, J, and K are paired with X, Y, and Z, so wouldn't it be Z?
Okay, let's see. A would be x equal 1. B would be y is equal to 1. And z is equal to z is equal to 1.
It'd be parallel, so it'd be A and B. Not
Wait,
C.
I put z rather than c. Okay. I went to Zaxby's and got my number. Okay. Z equals 1. Okay. Now, the vector k is normal to which of these planes?
I would say A and B.
Okay. X equal 1 is here, and the vector k would be parallel to that. So you're absolutely right. X equal 1. Come out 1, and it's parallel to the YZ plane. The k vector is up the z plane. That's going to be parallel to it.
You mean perpendicular?
Yeah. Normal to would be perpendicular to it.
Right.
It's going to be, the vector k is going to be parallel to that. Y is equal to 1 would be this plane right here, not the origin, not the plane here, but come out 1 from it. That's also going to be parallel to k. So it leaves z equal 1. Z is equal to 1 is going to be
Okay, so
this way. The first time you had it right. It's perpendicular. So that would be c, which is z is equal to 1. Second?
K goes along the Z axis.
Right, the z-axis.
Plane Z
is going to be perpendicular to that axis. So it's C, Z is equal to 1. Perfect, they got it right. Number 3. Okay.
Oh, I didn't know this one was for free.
Yeah, so the others are expensive, but this one's for free. Let me start a new page, because this has more writing to it than the other two did. Which of the following planes is not parallel to this plane? Here's the plane, x plus y plus z is equal to 1. And which of the following planes is not parallel to that? Okay? A would be, but it's A, okay. 2x plus 2y plus 2z is equal to 1. 2x plus 2y plus 2z is equal to 1. B would be, and it is, x plus y plus z is equal to 3. And C would be, if it were, x minus y plus z is equal to 0. X minus y plus z equals 0. Which one of those three planes is not parallel to that one?
Have to be C.
Did you say C? Yes, okay.
Yes.
Yes, it's Spanish, okay. Because
Too many.
this has a normal line, a normal vector 1, 1, 1. This has a normal vector 1, minus 1, 1. So they can't be parallel because they don't have the same normal vector. This obviously has 1, 1, 1 as a normal vector, just as a different location. The other one, all you have to do is divide everything on both sides by 2, 2, 2, 2, and then you have x plus y plus z is equal to 1/2. That's parallel to that. Okay? Pretty close, but not parallel, but it's still parallel. All right, so it better be, what do we say?
C.
C. Yes, we did. Okay. They like C's, okay? Very positive they are. Okay. And here's Nigel. Okay. Yeah, I'm going to stand in front of this light. It's a little warmer there than it is anywhere else. Okay. We're doing the preliminary questions at the end of 12.5. We've just done the first 3, and we're getting ready. Once I stared at the light, I can't see now. Number 4. To which coordinate plane is the plane y is equal to 1 parallel? Okay. To which coordinate plane is the plane y is equal to 1 parallel? Okay. Now, you just came in. What do we mean by coordinate planes? Either the XY plane, which would be the floor, the XZ plane, which would be this wall, or the YZ plane, which would be that one. Okay, those are the 3 coordinate planes. So which of those planes is parallel to the plane y is equal to 1? Yeah, the XZ plane, wait, yeah, XZ plane is this one, y is equal to 1 is here. So out 1 and then do that. Yeah, those are parallel then. So the XZ plane. And let's see what they call it in the back. The XZ plane. Good for them. They called it the right thing to boot. All right, now we'll do 5. Which of the following planes contains the z-axis? Okay, which of these 3 planes contains the z-axis? A would be z is equal to 1. B would be x plus y is equal to 1. And C would be x plus y is equal to 0. Okay, which of these, and these are, by the way, all planes, and which of these contains the z-axis? Now the z-axis, remember, is this one in the corner here. Right? What were you going to say?
We know A isn't.
We know A isn't because z is equal to 1 would be parallel to the xy plane, which would not contain, I mean, the z-axis goes through it at one point only, so it can't contain the entire z-axis. A's out. X plus y is equal to 1. And x plus y is equal to 0 are parallel planes, right? X plus y is equal to 1. Let me just draw the line. 1, 0, 0, and 0, 1, 0. That's on the plane, right? Okay. Yeah. That's where z is equal to 0. So that plane, no matter what z is, x plus 1, so that basically is the plane that does this, right? But x plus y is equal to 0, that would be, yeah, the origin would be on it, and x plus y is always 0, so that would be, yeah, that would be the plane that comes through like this. No, not like this. X plus y would be positive. It would be the one that goes through this way. The second quadrant and the...
I took it as we're in the first quadrant.
Yeah, we're in the first quadrant, right. So it's the one from x plus y equals 0. The x would either be negative and the y positive, or the y negative and the x positive. Wait, I didn't do that right, did I? Y negative and x positive. Okay. But anyway, those are saying the same thing. It's that plane there, but guess what? The z-axis is in that. It's going through the origin, and it's going up and down, so the z-axis has to be there. Okay, so it would be this one. Okay, because x plus y equals 0 would be the line that goes through the origin with a, that would be y is equal to minus x. So it has a -1 slope.
Oh, the axis. Okay, I was thinking we had to include the entire z plane.
No, not z plane.
I don't see any of these at work, but yeah, that one does
That's
contain
2,
the axis.
yeah, the z-axis. So that would be C. They like C, don't they? Okay. Yes, C. X plus y is equal to 0. Good for them. Now let's see B. I mean 6. And the answer is not going to be C. I'll guarantee you that. Okay, because it only has 2 choices. Okay, A and B. So suppose that the plane P with a normal vector n and a line L with direction vector v both pass through the origin, and that n dot v, the dot product of n and v, is equal to 0. What does that mean? Perpendicular to each other. Which of the following statements is correct? I'm going to clear off what we got here. This looks like this is going to almost take a drawing, and this is going to really be bad. Suppose that a plane P with a normal vector n and a line L with direction vector v both pass through the origin. Okay, so the plane P passes through the origin, and the line L pass through the origin. Okay? So the N dot V is equal to 0. Okay. Which of the following statements is correct? L is contained in the plane P, or L is orthogonal to plane P. Okay? All right. Now, the plane P passes through the origin, and so does the line. Okay? The vector that's in the direction of the line and the plane that has a normal vector in. They both pass through the origin, but the normal vector to the plane dotted with the directional vector for the vector, they're perpendicular to each other. So they both pass through the origin. Now this is a real simple case. Let's just say that plane P is the xy axis. So what would its normal vector be? It's going to be I, right? Or I mean, it's going to be the y-axis basically, or something parallel to the y-axis. I mean, anything parallel to the y-axis.
This is the xy plane?
I'm sorry, xz.
Okay, then
Did I say xy?
Yeah.
Okay, I'm sorry. Okay, let's do xy plane. Its normal vector is going to be k or anything parallel to k. Okay? Now, a line that has a directional vector v has to be orthogonal to that.
Oh, so it's going to be...
Yeah. So the only thing that's orthogonal to this is going to be in the plane. So it's got to be, is that A contained in P. The only thing that the origin does for you is guarantee it's got to be through there, so it is. Otherwise, it could be parallel to the plane. But if they both pass through the plane, that means it's got to be in the plane. So I think it better be A. Yeah, statement A. Good deal. Homework exercises. Do any of the odds 1 through 7. Do either 9 or 11 or both. Do either 13 or 15 or both. Either 17 or 19 or both. Any of the odds 21 to 27. Do 29. Do either any of the odds 31 to 35. Do 37. Do either 39 or 41 or both. Any of the odds 43 to 47. Any of the odds 49 to 53. Any of the odds 55 to 59. And any of the odds 61 to 69. Now, some of those are just think through or write them, or you don't have to write them, but think through the issues. Others I'll have calculations. If you really are fired up, you can try further insights and challenges. So, I'll leave that alone. Now, let's see, are there any more slides here? I think not. So let's discard those and move on to 12.6. I think this is the last section we do before we have our test. Okay? Probably should have already gotten this test ready. I can't remember if I did or not. I've got to check and see. Remind me, is this our first test in this class? Because I'm teaching so many different classes. So this one, we're doing 11.1, 11.2, and the section we're covering in 12. Is that right? What's that? Yeah, that's what I was thinking it was. Okay. So I'm pretty sure I don't have that one made out. should have had it done. I was thinking, well, we probably aren't going to finish this today, but I would have liked to have given you the weekend to work on it, extra weekend, but you're going to have all the time you need anyway. Sorry about that. I messed up your weekend. You could have been working on calculus. Now you got to find something else to do. Homework. Yeah.
So I will have plenty of that.
Okay. All right. Now, what's that? Okay. All righty. Current slide. Now, the topic here is a survey of quadric surfaces. What does that almost sound like? Quadric surfaces. To me, the first thing that pops to mind is quadratic, okay? It's not quite the same, but it's, it's sort of similar. Because a quadratic equation, the maximum exponent is 2. A quadric surface, the maximum exponent is 2. So in that sense, they're sort of similar. Now, this is by far the most extensive definition of a quadric surface you can give it. Okay? You have x's to the second power, y's to the second power, z's to the second power. Remember, maximum degree of any term has to be 2. So you can have x times y, y times a z, z times a x, and that covers all the cross terms, right? xy, yz, zx, okay? Okay, so that's maximum power of 2. You can also have linear, so you can have something ax, this is small a, this is capital A, ax by plus cc, cz, or you can have constants, but you can have second degree, first degree, 0 degree. And that covers it all, folks. Of course, the capital A, B, C, D, E, and F, the little a, B, C, and D, they can be positive, negative fraction, decimal, 0, rational, irrational. It can be any real number in the world. Let's not get into complex numbers with these beyond the real numbers. Okay? Now, the quadric surface is defined by a quadratic equation in 3 variables, just like a quadratic equation in 2 variables defines a parabola. The like conic sections, and we haven't really talked about those, did we? But you may have run into them sometime in your past, right? May or may not. Oh, we did. Okay. I couldn't remember if we did. Yeah. Yeah, I did. Okay, that was this class. I was thinking it was another class. Okay. Yeah. Okay. Now, these are quadric surfaces. Good deal. Here we have Jonathan. Okay, 4 out of 9 are here. We're getting close to 50%. Okay. Now, like the conic sections, quadric surfaces are classified in a small number of types when the coordinate axes are chosen to coincide with the axes of the quadric surfaces. I wish I just said that, of the quadric. Okay. The equation of the quadric has a simple form. The quadric is then said to be in standard position, and in standard position, you don't have any of these cross terms. The D, E, and F are all 0. That's what we're going with. We're not going to mess with any of those. Okay? So we're just going to live with these there. In fact, most of the time, we're probably even going to leave those at 0. Okay? But the D and the ABCs may not be. Now, some of them, you'll not have a 0 here, but you will. You'll have a 0 here, but not one there, or something like that. You'll see when we get there. Okay, those are the ones in standard position that don't have the cross terms. Don't have X, Y, Y. Okay. Now, and the linear part also reduces to just the constant term. Wait. In other words, and when it says the linear part reduces the constant term, that means these are zeros as well. Now, not always. Most of those are the ones we're going to deal with. There's a couple that one particular that we want. Okay. Now, before I, second, we're in 12.6, just the beginning of 12.6. Sorry about that. Right at the bottom of 670, top of page 671. Before we do anything else, though, I want you to remind me of a couple of issues. Name a closed, how would you call this? Shape, I guess, that we like to play with in a plane. Closed shape. A circle. Okay, let's start with the circle. Whoa, I forgot. Huh? I was trying to draw in a circle, but I forgot that I was in expanded mode. Okay, so if you got a circle here, now let's just imagine that's a circle. It's probably not, but pretty close. If that was a circle, what would be, and let's just put the origin right smack dab in the center. We'll call that standard position. What would be the equation of that circle in a plane? Say again? X squared plus y squared equal r squared. That is fantastic. Okay? Now, if that circle were translated anywhere else in the plane, then you would have x minus a squared plus y minus b squared, but still equal r squared. And that's where you would get some of your linear terms from. But in standard form, it's at the origin. Now I'm going to show you another way to express that. Okay? Let's divide both sides of the equation by r squared. Every term on both sides of the equation by r squared. And what does that give you? Perfect. Okay? That's also the equation of a circle. And in fact, you didn't have to call it r. You could have called it a, but then a would have been the radius. Okay? All right. The deal here are the two features to keep in mind, that that there's a plus sign in between the variables, the squares of the variables, and the answer here is 1, positive 1. Okay? And then whatever your coefficient is there, if they have this, your denominator's there, those are numbers. The variables are up top. Then that's if those are the same, that's a circle. Okay. Now, let's do a little something to that circle and make it not quite a circle anymore. In fact, it's probably one of these right now. You know what I'm talking about? Either squish it. Say again?
Sphere or an ellipse?
Oh, yeah, we're keeping two space. Let's do an ellipse. An ellipse is going to be something like this, right? Some way, okay? Not that funny, okay. All right. So this may be an A, and this is a minus A, this is a B, and this is a minus B, okay? All right. Do you know how the equation of that ellipse changes from what the circle was? What the circle was, this is plus r, that's minus r, that's minus r, meaning everything is r there. So in this case, it's x over a squared plus y over b squared, but it's still equal to 1. Okay? So this is the equation of a circle. Equation of an ellipse would be x over a squared plus y over b squared is equal to 1. And whichever is the larger, A or B, that's what we call the major axis, and the other one's called the minor axis. Okay. All right, those are our two closed shapes. Okay, we may have some others, but those are the two major ones. There is also a couple of open shapes. Yes.
You said that's the equation of the ellipse.
Oh, an ellipse. Okay, this is an equation of a circle, and this is in two space. Ellipse. Okay, equation of ellipse. Now, can you name me a couple of open shapes that you could have in a parabola? Is certainly an open shape. Okay. I'll just draw a real simple one there. What's its equation? Y is equal to x squared. That's the simplest. That's the parent function for most parabolae. Okay. Now, if we here's the big thing about it. Notice there, circles, ellipse, your variables, and their associated related constants are squared. Here, one is squared and one is not. Okay? That's the major thing to remember here. I'm going to cheat a little bit. Okay. Yeah.
Would it help if we did hyperbola instead?
Okay, hyperbola is the next one, and I wanted a little. So this is parabola. Okay, now let's do a hyperbola. And I'll try to do it over here. Tell me generally how to draw a hyperbola. All right, it's kind of like that. I mean, that should be the same distance from the origin, but you got the idea. Now you can also have them offset, but then you have your cross terms. But if they're going up an axis, then you don't have the cross terms. And really the minus should equal the plus there. Here's the easy way to fix that. I just thought of it. Okay. Rather than, how about that? Okay. That's a hyperbola. Does anyone know what the basic equation for a hyperbola looks like? Okay. It's x over a squared minus y over b squared is equal to 1.
So they just broke that ellipse up.
Yeah, you basically take an ellipse and do something like that. Okay. It has a minus sign in between. But both of the variable and their associated, by the way, this is plus a and that's minus a. And while the y's come into play here, and I haven't drawn these too well, but there is a line here that is asymptotic to this end and asymptotic to that end. Another line is asymptotic here. And basically, the y's have to deal with how steep or non-steep those are.
Close they get, I guess.
Yes, exactly. The asymptotic, that part gets close no matter what, but whether this is a big fat hyperbola or a skinny hyperbola or something, that has to do with the y. We're not going to mess much with that. But those are your four basic shapes. Okay?
Hyperbola might have feet.
What's that?
A hyperbola might have feet.
Might have feet?
Feelings.
Oh, feelings. Okay. All right. Now, there's something flying around here, too. I don't know what it is. There is one other thing, but it really doesn't have a shape that we need to worry about here. All right. Now let's move to 3 space. This is all in 2 space. This is all in the plane.
And that was all like square terms.
And
something like the cubic thing.
okay, not going there. not in quadric sections. Those would be cubic surfaces or something like that, and not going there at all. These are bad. I mean, these are fun enough. Okay. So, but keep in mind those four basic equations. Okay. Now we're going to first deal with an ellipsoid. Now, really, what we could have dealt with, but they don't, is a sphere. I think Cameron mentioned the sphere, and maybe someone else did too. But the thing is, we're not going to need a sphere. We're going to the ellipsoid. Now, what was true about ellipses? Every variable and its associated thing was squared, and you had pluses between them, and it was equal to 1. Same thing here, it's just 3 dimensions. Okay? Whereas now, this is in standard position, so the origin is right in the center of this thing. It's not on the thing, but it's in the center of it. And where the x-axis intersects here is the A and minus A, where the y-axis intersects is B and minus B, and where the z-axis intersects is C and minus C. Okay? That is your ellipsoid. There it is. Looks like a mosquito to me. Okay, sorry. Now, here's some things to notice about this. And this is using terminology from that last thing. Remember what our traces were? They were either the coordinate planes or things parallel to the coordinate planes. So let's talk about the traces for an ellipse. Let's say, which one you want to start with? The coordinate planes. XY, YZ, XZ. Which one? You name one. XY. The XY plane is this one here. Let's just take that XY plane and this symbol here that goes to the A, B minus A minus B, that shape there, guess what it is? An ellipse. That's because you see it's equal to 0 on the XY plane, right? So that coordinate plane gives you your ellipse that we had before. Okay? Pick another plane, any plane. XZ or YZ? YZ. Okay, the YZ plane is this plane here. X is equal to 0 here. So the YZ plane would have B, C, minus B to minus C. And guess what shape that is? Where X equals to 0, that's an ellipse on the YZ plane. So the trace on the YZ plane is also an ellipse. What's the one we haven't done? The XZ plane. And on the XZ plane, that's this one where Y is equal to 0. So it'd be A to C to minus A to minus C here. That shape right there, guess what that is? That's an ellipse also. Now, it almost looks like it's a circle. It could be if A and C are equal, then that could be a circle. But if these not, it'd still be an ellipsoid. But if Y is 0, if these are different, that's an ellipse if they're the same as a circle, which is a special case of ellipse. Right?
Couldn't a sphere be considered?
It is. That's why they don't do a special deal with it. It's just where the A, B, and C are all equal. Exactly. Okay? So those were our coordinate traces on the coordinate planes, but also traces are on planes parallel to the coordinate planes. So if you do an x equal, say 1 in here, as long as A is greater than 1, you slice here, you'll just get a smaller ellipse. And a smaller ellipse and smaller ellipse until you get x equal A, and you're down to a single point. But any trace on a plane parallel to the YZ plane, where x is equal to anywhere from minus A to plus A, the trace from that plane is going to give you an ellipse also. Okay? Same thing here. Any of these traces, and these traces, and any of those traces, and those traces will give you ellipses. So every trace will be an ellipse until you get to beyond A or minus A, beyond B or minus B, or beyond C or minus C. You'll always get ellipses. Okay? That's an ellipsoid. Sort of makes sense? Now, some places they call this analytic geometry. Okay? But they call it here just survey of quadratic surfaces. So, they say here, describe, example 1, describe the traces of the ellipsoid, and here's the, it's all wadded up, okay, of this. It will first tell me if indeed you think this is true. X over 5 squared plus y over 7 squared plus z over 9 squared is equal to 1. Okay? What shape do you think that is? An ellipsoid. Ellipsoid. It's three-dimensional. It's got all three variables in it. And it has
Different denominators.
each of these pairs are squared, pluses in between equal to 1. Ellipsoid. Okay? How would you describe this? Could that be this ellipsoid? What's wrong with that? If anything.
Which axis is which?
Okay,
Well,
this is X, this is Y, that's Z.
Z is much.
Okay, yeah. In this one, C would be 9, so it would have to be the major axis there. Okay? And then your Y would be minus 7 to plus 7, and your X would only be minus 5 to plus 5. So it'd be a football pointed upward, okay? Not quite a football, but similar to it. But a football, you expect those to be circular cross sections this way. This is elliptical, so this is not a very nice football. Okay. But that football would be standing on end, if that were a football. Now, the traces would be in everything as long as X was between minus 5 and 5. All those traces would be ellipses. The biggest one being on when Y is equal to 0, but the smaller ones being plus or minus, anywhere from minus 5 to 5. That would be, they would be ellipses. Getting smaller as you get closer to 5, the largest would be at X equals 0. Okay? Going the other way, the Y's can go from minus 7 to plus 7, and Z minus 9, plus 9. But every one of the traces parallel to any axis within those bounds is going to be an ellipse.
They probably have a picture for this.
You're right, I guess. No, they don't.
Weird disc thing at the bottom.
Oh, there they are. Yeah, that's it. You're right. Okay, so let's, here's a generic equation for an ellipsoid. Okay, I didn't blow it up. I should have. Boom, I blew it up. Okay. Here was your planar traces, or at least one planar trace, where Z is equal to, okay, that's not a plane. This is not a coordinate plane trace. This is Z is equal to Z0, something we're assuming greater than 0, and it still traces an ellipse as long as you get, say, less than C up there. That would be an ellipse, so that's what we were talking about there. Yeah, they had them out of order. That's it. Okay. So, your coordinate plane traces are from, which one you want to do first? The X would be minus 7, 5 to plus 7 to minus 5. You know, making your way around here. The XZ plane, XY plane, the XZ plane, which is this one, you would be going to lavender line, whatever that is. That's probably magenta line from 9 to 5. That's probably part of something, by the way. -9 to -5. That would be your ellipse. Coordinate plane ellipse of that one. And then the green one is the YZ plane. And that's from 7, Y is equal to 7, Z is equal to 9, Y is equal to minus 7, Z is equal to minus 9. That's that. Now that looks almost circular. It's not. It's a little elongated on the Z-axis. Squishing a little bit on the Y-axis. So that is your ellipse. Those are your coordinate plane traces. If you did the horizontal traces, meaning parallel to the XY plane, they would be all the way up to less than 9 and greater than -9. Your vertical traces, you have two sets, one parallel to the XZ plane, those are the magenta ones, and the ones parallel to the YZ plane, those are the green ones coming out here, corresponding to these two blues. So they usually just call them horizontal traces and vertical traces, keeping in mind you got two sets of vertical traces, only one set of horizontal traces, assuming Z is always your vertical axis. But you can have traces along the x-axis and traces along the y-axis, and both of those are vertical traces. All right, does that make sense? That's describing them. All you had to do was draw pictures of them. That was fun, wasn't it? Okay. Now, if I ask you, or if the book asks you to give the equation of one of these ellipses for one of the traces, either vertical or horizontal, what you'd have to do, you'd have to be given what the y value was, something between -7 and +7. It has to be between there. Anything beyond there, there's no traces. Not a trace, okay? But if there's anything inside that, then what you do is, for that y equal whatever value that is, say 5, it would be 5/7 squared, it would be 25/49. Subtract that from 1, and now you have an ellipse of that size. Okay? And so it makes it a smaller ellipse. Okay? You'd have to do a little bit more monkeying around, but it's doable. It'd just be a constant though. Does that make sense? Now, ellipsoids, what was one of our open shapes? Hyperbola. Let's now go to hyperboloid. There's actually 3 types of hyperboloid. Well, there's 2 types of hyperboloids and one kind of special case that we'll get to next. Hyperboloids. Here's the picture of these hyperboloids. Oh, wait. I forgot. Remember, we had to pass over one of these slides because I had them out of order. Here are your equations for your hyperboloid. Now, what was it that was true before for hyperboloid? It was a x over a squared minus y over b squared is equal to 1. Right? Well, I wish they had done it the other way. 2 of the variables, it doesn't matter which 2, they just chose x and y here. They do have a plus in between, but if you had moved this to this side, that would have then been a minus d over c squared, and this would be equal to plus 1. This one is equal to minus 1. Okay? Now, let's talk about what those would mean, okay? A paraboloid of one sheet, okay. If z was either 0 or a constant, let's take it as 0 now, what do you get in the xy plane? And everything parallel to the xy plane. In other words, those horizontal traces. What is every one of those? That's an ellipse, right? That's an ellipse. If z is equal to 0 or z is a constant, it would just be smaller ellipses. Oh no, actually bigger ellipses going up and down, okay? Depending on the size of z. Okay. Now, can z equal 0 here? That is the question. Can that be true? Ever. Why not? That's always positive. That's always positive. You're adding them together. You can't get a negative number there. So z cannot equal 0. Okay? So the -1 there cuts out the possibility of z ever being 0. Okay? Or if you move the z across there, you know, same type thing. But anything
below 1.
All right. Anytime that z over c is greater than or equal to 1, so let's do it greater than 1, then this is going to trace into an ellipse. But it's got to be greater than or equal to c. So the two-sheet hyperboloids are going to start at -c and +c. By the way, this is your axis. The one that has, if these are moved over here and where your minus sign, this is the axis for that hyperboloid. Okay? You could have this y, that z, this be x, and the x would be your axis. One sheet or two sheets to the wind. Okay? Now, so that's what your equations for the hyperbola are. Here's what they look like. Now, keep this in mind. Now, let me back off and say this. What happens if y is equal to 0, especially in that top case? Now you have x over a squared minus y over z squared is equal to 1. That's a hyperbola. So when anything parallel to the y-axis, y is equal to 0 or y is equal to any constant there, then that's going to be, your traces are going to be hyperbolas. These traces are going to be ellipses. These traces are going to be hyperbolas. Those traces are going to be hyperbolas. So that's why they call it hyperboloids. Okay? And these will be ellipses once you get z equal to c or greater, or minus c or less, then these will be ellipses. That would be hyperbole, and that would be hyperbole. Okay? So let's see what they look like. That was the ellipsoids. Here are the hyperboloids. One sheet and two sheets. One of them is a fitted sheet. No, never mind. Okay.
I was wondering how many sheets of paper do we need?
Okay. When you start doing these, you'll think it's a huge waste of paper. So notice here, this is with the z over c term being the minus one, or on the other side of the equation, equal sign, then that's going to be your axis. And that's your axis. So these are the ones shown that we have before. If the x over a was the negative one on the other side of the equal sign, then this would have been your axis. The y, that would have been your axis. You just flip this around, whichever way you want it to go. This is the one sheet. And notice here, every trace, either on the xy plane or parallel to the xy plane, your horizontal traces are going to be ellipses. Every one of them. Okay? Your vertical traces, the way they've done it here, these are hyperbole. Except for one, right here, you get the intersection of two straight lines. Strange but true. And over here, you'll also find one, it's just hard to see. But all the rest of these are going to be ellipses. They only drew this one here and then your straight line, and then you can't really tell what. There's one. Ooh. There's one. It's hard to see them here. Here's one, and there's one. They don't even seem like they fit, but they. I'm sorry, it's on the wrong axis. Okay. The other axis is hard to see at all. The vertical traces along as you go up and back parallel to the YZ axis are then the green ones. And again, they are hyperbole. Okay. The two sheets where you have that -1 out there, then remember the Z over C has to be greater than or equal to 1. When that's equal to 1, you have single points here. Anything greater, then you have, again, your horizontal traces beyond, outside of plus and minus C, are all ellipses, okay? Your vertical traces are all hyperbole, okay? And both the magenta ones and the green ones, all hyperbole. Okay. Hyperboloids of two sheets. One of your variables, if you write all the variables on one side and numbers on the other side, then all the variables, you have 2 being plus and 1 being minus. The minus one is your axis, and the plus one will create the ellipses when you do your traces, and the vertical ones will all be vertical traces will all be hyperbole. Now, if you have two sheets, then you have a -1 on the other side, but everything else looks the same. Okay. Does that kind of make sense? All right. Let's see if we're skipping anything. Yeah, example 2. The traces of a hyperboloid of one sheet. Okay. Let's see. Yeah, I think this is it here. Determine the traces of the hyperboloid. Here we have it. I'm going to blow this up for now, but if I write anything, I'm going to have to bring it back. All right, here's your hyperboloid. X over 2 squared plus y over 3 squared. I like to write this minus z over 4 squared is equal to 1. They like to put z over 4 on the other side. Now, because that's a +1, you don't have any problems with anything here, really. Okay? The 2 represents on the xy plane, that's where the x, that's as close as this first hyperbola reaches at 2, 0, 0 and stays on the xz plane from then on. And minus 2, 0, 0, and the y term is always, y component is always, y coordinate is always going to be 0 on the xz plane, and your x's and the z's vary. Okay, but at that point the z 0 also, so it's +2 and -2. Okay, on the yz plane, I'm sorry, xy plane, you have the ellipse here going from 2, 0, 0, 0, 3, 0, negative 2, 0, 0 to 0, negative 3, 0. That's the ellipse here. And every trace, horizontal trace above and below that. It's also an ellipse, but they're getting larger as you go. Because as Z is increasing, this number over here is getting bigger, so your ellipses are getting bigger. So this is a hyperboloid of one sheet. That's what the horizontal traces look like. All are ellipses. Okay, your vertical traces on the XZ plane, that's the magenta ones here. The YZ plane, that's the green ones here. And then any that you go inside that, well, let's do outside that first. Outside of this, then you're going to have let's start at origin on the XZ plane and come out positive on Y. Okay, here's the first one you have on the XZ plane, the magenta one. As you go out from there, then yeah, okay. Here is that doing things on three-dimensional things. Drawing two-dimensional, three-dimensional graph is just a pain in the neck. Yeah, here's the first one. The same one they did here. That one and that one. That's it right here. Here to avoid. You can't see the ones on the back side. Sorry about that. Yeah, smothered with everything else. Then as you go remember, your Y is always 0 here. And as you go decrease your X's, you've got hyperbole that are doing like this. You know, it's really hard to picture here. But then when you get past here, your hyperbole are doing like this. Now these are still your vertical ones here. They're hyperbole like this going out, and then at some point they flip and do that because they run out of Y here. Okay? Same thing with the green ones. They don't show as many of these, but here is the one they show right here. That's this one here. That green one there. You can't see the one back there. Any Y less than that, they're going to be inside that until you get here and they cross at that point, and then they start going down like this. They look like they're in a different plane, but they're really in the correct plane. It's just, but they're always hyperbole. Anything you do in the vertical here, perpendicular to the axis, are going to be hyperbole. Parallel to the axis, those traces are going to be ellipses. Ellipses. Okay. Not particularly easy to draw. Okay. This is your hyperboloid of two sheets. Okay. Now they did two things differently here. Can you tell me what they are?
That's generic.
No, yeah, this is generic form. But what they've done, they put the Y as either the negative one or on the side with the constant. That makes the Y the axis of that hyperbole. The -1 then makes it two sheets rather than one sheet. Okay? What's that?
They just like using paper.
Yeah. Right. Now, the other thing is any trace along the axis, parallel to the, perpendicular to the axis, those are when you're defined. Not defined for B less than Y or minus B greater than Y. In between minus B and B, there are no traces. It doesn't cut there because then you have plus equal negative. It can't happen. But once you get to Y is equal to B, then you have a single point plus b or minus b, where that's equal to 0, and then anything beyond that, either less than negative b or greater, those traces are going to be ellipses again, okay? Depending on the sides of A and B. A and C, sorry about that. All right.
So, when these things aren't on an axis,
I mean, like you have,
they're going to be in some kind of other.
yeah. Then you have the cross terms. The E, D, E, and F, X, Y, Y, Z, and yeah, you have those in there. And anytime they're off the origin being the center, then you have the linear terms for those translations. We're not going to do any of those, I hope. Okay. All right. But you see what you have here are hyperbole green, hyperbole magenta. Okay. It's hard to see over here. You can see those on that side easier than you can the ones on this side. The green ones are easy to see this way. The magenta ones are easier to see that way, this way, and the green ones this way. So that's what your traces look like. It's hard to call them vertical and horizontal now. I'd say traces perpendicular to the axis and traces that are parallel to the axis. That's the best way to say this. A perpoloid of two sheets has the -1 for sure. Hyperboloid meaning one of the variables. They're still all three squared, they and their associated term, but one of them is negative something or another. C over D squared, Z over C, yeah, whatever. All right, now the elliptic cone. Again, I don't like particularly the way they write this. How I like to write this one is put the minus D over C squared here, and what's it equal to? 0. So not a 1, not a -1, but a 0, that's going to form the elliptic cone. Why do we call it elliptic? Because all this being 0 being the axis of that cone, all the horizontal traces are going to be ellipses, okay? And your vertical traces still are going to be the one at the center. Let's see, let's get a picture of it. And let's see. This is somewhat bizarre here. I see example 3 as a hyperboloid of two sheets, and figure 7, no. Oh, that was the one we were just looking at. These have no numbers with them. Okay, we were looking at this, that other one before. Sorry about that. So here's the elliptic cone. There's the equation about a third of the way down, page 673. Here is the graph of that. Okay. Now, what does this look like it might be a kind of a limiting case of? Okay. Let's think of this. The hyperboloid of two sheets would have had a +1 on this, right? I'm sorry, one sheet. Hyperboloid of one sheet would have had a +1 here. Of two sheets would have had a -1. Okay, one sheet, has ellipses everywhere here and hyperbole everywhere there, but it has a waistline. Okay. Now, two sheets, nothing in there. That's with a -1 there. Okay. This has a 0 there. So it's in between the +1 and the -1. Basically, you shrink that waistline down until it's nothing. Yeah, the origin. And then anything past that, they separate and start moving up. But they're rounded. So that's not quite fair, but it's getting close. Okay? Notice what your horizontal traces are here, as long as that's your axis, the vertical is your axis here, your horizontal traces are all ellipses, okay? Your vertical traces are all hyperbole, okay? Except, of course, at the origin and at the planar traces, the coordinate plane traces, then you just have a cross, okay? And the steepness of the cross depends on the relative size of this A and B, okay? A and C, and B and C, and the substance. The A and B, that tells you the ellipses, but the A and C and the B and C, that tells you something about the slope of those lines, where they cross on the origin. Okay. Does that kind of make sense? All right. Now, ellipsoids, hyperboloids, two kinds of those, one sheet, two sheet, elliptic cones. The final thing is your paraboloids. There are two types of them too. Now remember what we meant by a parabola? A parabola had one variable with a square, the other variable in linear. Now, if we have the axis vertical, then your linear axis is going to be the z. Okay? Just like your parabola, its axis with the y-axis, y is equal to x squared. If you have x equal y squared, then the axis with the x. X equal y squared. So z equals something squared. You can flip these around and it'll be fine. Now, the elliptic paraboloid, of course, when z is any positive number, or z is 1 here, that's going to be, yeah, those will trace ellipses, right, yeah. And any number z there, any positive number z there. Because notice here, z cannot be negative, because that's a square, add 2 squared, you're always positive. The closest you can come is x equals 0, y equals 0, z equals 0. The origin is on it, but nothing else is. Now the origin's there, and then as you go up the z-axis, you can't go down the z-axis, because z can't be negative. Up the z-axis, you get ellipses going up. So that's an elliptic paraboloid. Your traces, vertical traces, that's going to be a parabola. That's going to be a parabola. Parabola in the YZ plane, parabola in the XZ plane. Okay. Z always be the axis. Okay? How about that hyperbolic? Oh, is it time already? Oh my, we were just beginning to have fun. I thought y'all were just getting antsy or something. I couldn't imagine that. So we'll start over with the paraboloids next time. Oh, let me give you a few homework exercises here. Okay? Any of the odds 1 through 5. Any of the odds 7 through 11. Any of the odds 13 through 19. Do 21. Maybe 23. Yeah, 23. 25. Stop at 25. We'll pick up the rest of those next time. Good deal. Glad y'all could make it. Hope you have a good weekend. I was telling the others earlier, before some of you came in, I'm not going to be on campus during office hours tomorrow or Friday, because I've got to go to Dallas, Texas for a wedding. So we'll be flying out tomorrow afternoon, so that eats up all my office hours tomorrow and Friday. So I'm taking personal leave tomorrow afternoon. Huh?
You don't come to school Monday, do you?
Yes, you do. Yes, we do. Yeah. This is a high school. High schools, I think they all close on Monday, Columbus Day, but That's not one of our holidays. Sorry about that. Oh yeah, that was something that Cameron found, and he had asked me to announce it. I forgot to. That's going to be on the Birmingham campus. I think that's next Tuesday. Is that right? What is the day? Today's the 5th. Yeah, so Tuesday will be on the Birmingham campus at the ACAT building from 1 to 3. Wednesday will be here on the Veteran campus, Ethel Hall Auditorium. That newer looking building across the parking lot is Ethel Hall. To get to the auditorium, go around, take the road around the side, you go up a level, come in the big double doors that way, and it'll be immediately on your left. Okay. So yeah, I think Cameron said he would be leaving early to go to that. What's that?
I'm going to
Birmingham campus on
Are
Wednesday.
you talking about scholarship opportunities?
Yeah, and they have bunches of colleges here. Bunches of colleges.
University of Alabama, UAB, Troy, University of North Alabama, West Alabama, South Alabama, University of Memphis.
Yeah, even Birmingham Southern, I think, is there. Yeah, there's a lot of private schools as well as public schools. Yeah, great opportunity. Don't let it pass you by. If you're planning to stay in state, you don't want to miss that. Unless you want to come to my class and then go a little late to it, that'll be fine too. Okay, take care.